All right, welcome to The Explainer. Today, we're tackling something we use every single second, but maybe don't fully understand: electricity. We're going to peel back the curtain on this invisible force that, powers literally everything.
I mean, think about it, right? You flip a switch, a light comes on. You plug in your phone, it just charges. It feels like magic, doesn't it? But it's not. It's pure physics. So the big question is, what is actually happening inside those wires?
Okay, so it all boils down to one super tiny but super important character: the electron. This little negatively charged particle, it's the absolute star of our show today. Really, if you want to understand electricity, all you need to understand is what it takes to get these little guys to move. So where do these electrons live? Well, they hang out in what's called the valence band. The easiest way to picture this is like their home base. It's the outermost shell of an atom, and because they're on the edge, these electrons are kind of loosely attached, which makes them the perfect candidates to get up and go for a walk. And where are they trying to get to? Well, they're aiming for the conduction band. Think of this as a super high-speed freeway for electrons. If an electron gets just enough of a little push, enough energy to make the jump from its cozy home in the valence band, it lands on this freeway and is suddenly free to just zoom around. And that movement, that big rush of electrons, that's what we call an electric current. Okay, so that raises a question, right? Why can electrons just cruise through a copper wire but can't move through, say, a piece of rubber? Well, it all comes down to the size of that jump we just talked about. Physicists call it the forbidden energy gap. In something like copper, a conductor, the valence band and the conduction band are basically overlapping. There's no gap. It's an easy hop. But for an insulator, like rubber, that gap is huge. It's like a giant canyon they just can't cross. And then you've got this middle ground with semiconductors like silicon, where the gap is small. It's possible to cross, but they need a little convincing. All right, so we get it. Electrons need to move to create a current. But what makes them move? And what controls how they move? Turns out, it all boils down to this fundamental trio of forces. First up, we have voltage. And the absolute best way to think about voltage is just pressure, electrical pressure. You know how water pressure in a hose pushes the water out? Voltage does the exact same thing, but for electrons. It's the push, the potential difference, that gets those electrons moving. Simple as that. No push, no flow. And that flow we keep talking about, well, that is current. We measure it in amps. So, if voltage is the push, then current is the actual flow rate. It's how many electrons are zipping past a certain point every second. It makes sense, right? More push, more voltage usually means more flow, more current. But, in the real world, nothing flows perfectly. Every single material puts up a bit of a fight against that flow, and we call that opposition resistance. Let's go back to our water hose analogy. Resistance is like pinching the hose or having a narrower section of pipe. It restricts the flow. And this opposition, this friction, it generates heat, which, by the way, isn't always a bad thing. It's literally how your toaster makes your toast. What's really cool is that these three things, voltage, current, and resistance, aren't just random concepts. They're all perfectly connected by one simple but incredibly powerful rule: Ohm's law. It basically says the amount of push you have, the voltage, is always directly related to how much is flowing and how much that flow is being resisted. The magic is, if you know any two of them, you can always figure out the third. It's pretty much the golden rule for any electrical circuit. Okay, so now that we've got the fundamentals down, let's talk about the two main ways this current actually shows up in our world. You've definitely heard of them: AC and DC. So direct current, or DC, is the easy one to picture. The electrons just flow in one steady, constant direction. Think of it like a river, always flowing the same way. This is the juice you get from batteries. But then there's alternating current, or AC, and this is the stuff that comes out of the outlets in your wall. Here, the electrons don't just flow one way. They actually wiggle back and forth, changing direction super fast. Now, because AC is constantly changing, we need some language to describe its rhythm. One complete back and forth wiggle is called a cycle, and the most important thing to know is the frequency. That's just how many of these cycles happen every second. So the power coming out of your wall, it's probably alternating back and forth 50 or 60 times every single second. Pretty wild.
All right, so we've got our key players, voltage, current, resistance, and we've got our two types of current, AC and DC. But what happens when things get complicated? Circuits with tons of different paths and multiple power sources. How do we predict what's going to happen? Well, thankfully, electricity isn't random. It follows some very, very strict rules.
To figure out these complex circuits, engineers use a set of traffic rules called Kirchhoff's laws. The first one is basically just common sense, right? It says that whatever amount of current flows into a junction or an intersection has to be the same amount that flows out. Nothing just disappears. The second law is all about energy. It says that if you trace any complete circle or loop in a circuit, all of the voltage boosts and voltage drops have to add up and cancel each other out, equaling zero.
And for the really messy circuits, the ones with a bunch of different power sources all working at once, there's this really clever trick called the superposition theorem. It is a classic engineering move. You take one big, hairy, complicated problem, and you break it down into a bunch of small, easy-to-solve problems. You just look at what one power source is doing, then the next, and when you're done, you just add all those individual effects together. Simple, but powerful. Okay, enough theory for a minute. Let's bring all this back into the real world. How does this whole system of electrons, currents, and these fancy rules, how does it actually get power to your house and run your city? Well, the power that comes into your home is called single-phase power. It's a pretty simple two-wire AC system, and it's absolutely perfect for running all the stuff you use every day. Your lights, your TV, your computer, all of it. But when you get to the really big jobs, I'm talking factories, massive data centers, or even the entire power grid that connects our cities, we switch to something else. We use three-phase power. This stuff is the heavy-duty workhorse of the electrical world. It delivers a way more powerful and way more efficient supply of electricity. So what's the big deal? Why is three-phase so much better for the heavy-duty stuff? Well, the secret is in how it delivers the power. Single-phase power, the stuff in your house, actually pulses. The power level drops to zero many times a second. But three-phase power uses three overlapping waves. This means it delivers a smooth, constant, uninterrupted stream of power, and that makes it way, way more efficient for running big, heavy machinery.
And there you have it. From the tiny, tiny jump of a single electron across an energy gap, all the way to the complex rules that let us design circuits, and finally to the massive three-phase power grid that literally runs our entire civilization. It's amazing, really. We've managed to take this totally invisible force of nature and harness it to build our world. It kind of makes you wonder, doesn't it? What on earth will we power next?